Hello and welcome back. We'll continue on in section 4.2. Now we'll look at the multiplication rule as opposed to the addition rule. So the first thing that I have to start out with is the fact that I'm going to be writing P of A and B, and I'm going to mean something different than I meant in the previous video. This is sadly a little bit frustrating in mathematics when this happens, but we'll just have to distinguish between the two things. So P of A and B, as before, it meant that we had two events A and B, and they occurred at the same time, meaning in the same procedure, or maybe a better word here is in the same trial. As in, you roll one die, and you ask, does it belong to event A, which maybe is rolling an odd number, and event B, which is rolling a 4 or bigger. So those two things happen at the same time in the same trial. But now we're going to be looking at something different. We're going to be looking at doing one thing and then doing another, as in we have two different trials. Maybe it's the same procedure, maybe it's two different procedures, but the idea is that we'll do one and then another. So A corresponds to, say, from the first trial, and then B will correspond to the second trial. So this is a slightly different. So then if we could imagine, say, like maybe A is rolling a 6 and B is rolling an odd number. In this new scenario, the probability of A and B would be we roll 2 dice, and then probability of A and B is the probability of rolling a 6, and then on the second die, rolling an odd number. So again, this is just either repeating the same procedure twice, maybe varying it a little bit, making it two different procedures, but it's one trial and then another. So some more notation. We have the probability, this is where the probability of A given B. So probability of A given B is how we would read this out loud. And what it means is, so when I say A given B, I mean, what's the probability that A happens if we already know that B happened? If we're told, we flipped a heads on the first coin flip, what's the probability that we flip another heads? When we want to look at the probability of A occurring and then B, it's exactly what I just said. We think, what's the probability that A occurs? And then once we know that A occurs, what's the probability of B? And when we write this and in here, this means that we're going to be multiplying our two probabilities. So again, this is the probability that A occurs and then B. Probability that A occurs, and then once we know that A has occurred, we multiply by the probability of B. So before I do some specific examples, I want to point out that A and B might not affect one another. So for instance, in the example that I was just talking about, let's say that we flipped 2 coins, and A is the event of getting heads, and B is also the event of getting heads. Well, whatever I flip on the first coin, it doesn't affect the flip on the second coin, and this is called independence. So we say that A and B are independent, specifically if the probability that A occurs doesn't affect the probability that B occurs. They may interact with one another, but their probabilities are not affected. If their probabilities are affected, they're just called dependent. So what I'll do now is I'll go through an example calculating the probability that A occurs and then B, and I'll do an example where they're independent and an example where they're dependent. So this is a nice example. We're going to be drawing balls out of a bucket. And maybe there's a prize if you draw a red ball. So we have to reach in with our eyes closed and pull one out at random. 45 of the 50 balls in the bucket are blue, and there's only 5 red balls. So there's 2 ways that we could draw 2 balls out. So maybe we've paid for 2 tickets to attempt to win a prize here. There's 2 ways that we could do this. We could either draw a ball out, look at it, and then put it back, mix it up, and then draw a new ball. So this is called with replacement. After you draw the first ball, you put it back. So when we're talking about something with replacement, we sort of reset everything after the first go. Or after we draw the ball out, we hold it in our hand and we reach in with our other hand to draw the second one out. This would be without replacement. We're not putting the ball back in to the pool to draw it out again. And these are just a good example of independent and dependent events. So first of all, let's look at situation 1 where we replace the ball that we drew out. So what I've called these events are red 1 and red 2. Red 1 being we draw a red ball on the first for the first one, and red 2 being we draw a ball on the second one. So the probability of red 1 occurring, as in we draw a red ball on our first go, well, there's 5 red balls out of the 50 balls in the bucket, and each one is equally likely, so we can just divide. So 5 out of 50, that's the same thing as 1 out of 10, or 0.1. Okay, so we're in the with replacement scenario. So if I put that red ball back in, we've now reset everything. So the probability that we draw a red ball on the second go, well, there's still 5 red balls in there out of the 50 total, which is again 1/10, which is the same thing as 0.1. So now, with our multiplication rule, what's the probability of drawing a red ball and then drawing a second red ball, as long as we've replaced the balls? Well, we just get to multiply these guys. It'll be the probability of drawing a red ball first, and then the probability of drawing a red ball second, which is going to be 1/10 times 1/10, same thing as 1/100th, or 1%, 0.01. Okay, so that seemed pretty easy. We didn't have to think very hard with this one. Now let's do the without replacement. So the probability of drawing a red ball first, again, there are 50 balls in the bucket and there are 5 red balls. Each one is equally likely. 5 divided by 50, which we saw is about 0.1, or is exactly equal to 0.1. So now we're in a slightly different situation. We're not going to put that red ball back in. And we want to know what's the probability of drawing a red ball on the second go. Well, after we drew a red ball out, there are only 4 red balls left in the bucket. Next, I need to know how many balls are there total. Well, I've drawn one out, so there are only 49 balls left in the bucket. And from here, and again, I really want to emphasize that this is drawing a red ball in the second go, provided that we already know that we drew a red ball first. If we didn't know what color we drew, this would be a different calculation. But because we knew that we drew a red ball, there are only 4 red balls left out of the 49 balls left in the tub. And then again, our multiplication rule will take the probability that we draw a red ball times the probability that we draw a second red ball, given that we drew it on the first go. And this will be a slightly smaller percent than this. 40 divided by 49 is slightly smaller than 5 divided by 50. So this will in fact be slightly smaller than 0.01, but not by very much. So what happened here, we kind of noticed that drawing a red ball in the second go wasn't really affected by drawing a red ball in the first go when we replaced it. These guys are independent. Essentially, if you replace what you drew, or if you replace what you pulled out of the population, you've reset everything, and the probabilities haven't been affected. However, if you do not replace, depending on what color you drew first, it will affect the probabilities of the second one. So the probability of that second draw depends on the color of the first one. Therefore, it's dependent. And this will be true in general. When you do selection with replacement, it is independent. If you replace everything, you've reset everything, and it won't affect the next go. But if you don't replace things, now what you select or what you pull out of the population is going to be affected, and it's not going to be independent anymore. However, there's a caveat. If the sample size, so quite often this is important when you're drawing a sample from a population. Let's say we want to poll Americans, and we have to pick a sample of the American citizens to poll. There's so many Americans that if you pick your sample, if you pick one person, it really isn't going to affect the probability very much of picking anyone else. So provided that the sample size that you're picking is 5% or less of the entire population, it's so close to being independent, we can just call it independent. So to really drive this home, let's say that we want to ask Montanans if they played sports in high school. So we want to pick a sample. This is just for maybe a small class project. So we're just going to pick five people and ask them if they played sports in high school. Well, there's about 1 million Montanan residents. So the question is, how likely is it that each of the 5 people that we ask participated in a sport in high school? So we'll assume that, let's say, 20% of Montanans played some sport in high school. So the way that we think about this is we pick the first person and we ask, did you play sports in high school? Well, the probability that they did is about 0.2. So then we go to the next person and we ask them if they played sports in high school. Well, if the first person played sports in high school, that means that there's one less person that played sports, which means that it's a little bit less likely that the second person will have. But there's 1 million people in Montana, so removing one person from the population isn't going to affect things much, which means that for the next person, we can also assume that they had a 20% chance of playing a sport in high school. And then the third person, and then the fourth person, and then the fifth person. So the probability that the first person played sports, and then the next person played sports, and all the way out to the fifth person is just going to be 0.2 times 0.2 times 0.2 times 0.2 times 0.2. The product rule here just adds up. So this will be 0.2 to the fifth power. And I'll continue going through some examples like this in the next video.